Okay, so we're going to continue with our discussion of maximum likelihood functions and how to do maximum likelihood estimation. So in this example, we're going to look at the normal distribution. Normal distribution is very common for us to encounter, but essentially we want to think of this as like, how did we derive some of our formulas that we use for our estimations? And this is so one of the approaches that we can use in order to derive those general formulas. We're going to look at this in the context of a specific example. Now, in this normal distribution, there are actually two parameters that we have to solve for. And so it is going to require multivariable calculus for us to actually do the solving. But let's consider we have 15 students, and I measured their heights, or somebody measured their heights, and those are our XI observation values, and I've listed them here, and I've measured them in inches in this case. And so in each case, the measurement is taken and we plug these in to our distribution function. So in this case, the normal distribution is given by 1 over the square root of 2 pi times sigma e to the x minus mu squared all over 2 sigma squared. And I plugged in 69, my observation, for my x value. And my second observation was 72. So again, I don't know my two parameters, but I do know my x. So I plug that in. And so I continue with this for all 15 observations. According to my maximum likelihood function, I multiply all of these outcomes together. That's what the pi stands for. Capital Pi is product, stands for product. So I multiply all of these. And so I get this crazy expression. This nearly killed my word. And by nearly, I mean it actually did several times. It had to be reinstalled. It was terrible. Word is very unstable when you have equations that are this long. But I probably should have used a smaller sample size for this example. But this is what we get. And then when we simplify, we combine our 1 over the square root of 2 pi times sigma and combine our exponential functions. What we end up with is this expression. So we had 15 terms, 15 of these total terms. So that means we're multiplying the square root of 2 pi times itself 15 times. So 2 pi to the 15 over 2. Again, 15 copies of sigma. And then 1 over, in the exponential, we add up the exponents. So we have negative 1 over the square root of 2 sigma squared. But then we're adding up our xi minus mu's. So adding 69 minus mu quantity squared. And there's 3 of them, so I shortened it a little bit. 72 minus mu quantity squared, 75 minus mu quantity squared. I have 2 66s, so I have 2 copies of those. I have 2 68s, so I have 2 copies of those. Again, the order is not so much important so much as the correct count of things. Now, once we have this maximum likelihood function, just like with the one variable case, we want to take the derivative and set it equal to 0. But because we have 2 parameters to solve for, mu and sigma, we actually have to do partial derivatives. And so let's go look at that analysis. So this was our formula that we derived for, and again, I've left it in this sum of xi minus mu squared for the time being. It's a little bit more compact than putting in the exact values right now. And we can actually substitute them in after we've simplified the formula a little bit. Now, as I said, because there are 2 parameters we have to solve for, we have to take 2 derivatives. So the first derivative that we're going to take for this function has to do with taking the derivative with respect to mu. Now that means that all of this stuff out here that doesn't contain mu is just a constant, doesn't do anything. When we take the derivative for the exponential part, that has a mu in it. So that's going to need a chain rule. So we copy down the exponential function, and then the derivative of the exponent is essentially going to be, we bring the 2 down because it's mu, some expression with mu squared. We bring the 2 down. This coefficient is still out front. The sum, and then we take the derivative of this expression, and we actually get, this actually should be a positive because there was a negative here already, and this negative in front of the mu will make this a positive. It's a constant. It's not going to make a difference in the long run, but it is a typo. And then the second thing that we're going to do is we're going to take this derivative of the same function, but with respect to sigma. Now, this is going to be a little trickier because there is a sigma in the coefficient, and there is also a sigma in the exponential. So that's going to require a product rule. Again, the 2 pi to the 15 over 2 is not going to do anything. It's just a constant. But this is essentially sigma to the negative 1/15, negative 15. And so we get a negative 15, and then it becomes sigma to the negative 16, which is positive 16 in the denominator. Copy the exponential, and then copy the coefficient, take the derivative here. And then when we take the derivative here, again, we're taking the derivative in the exponent. So this is, again, 1 over 2, but it's sigma to the negative 2. And so when I take that derivative, it cancels out my negative sign, but I get a 2. And then this sum part doesn't actually have any sigmas in it. And so it's just like a constant as far as sigma is concerned. And again, we set that equal to 0. Now, with the derivative with respect to mu, this can't be 0 because the only variable we have is in the denominator. Exponentials broadly cannot be 0. And so that leaves us with this expression. Again, this should be a positive, but because it's equal to 0, it won't matter. That leaves us with this expression, though, to be equal to 0. And in the second one, in the sigma example, again, we have to do a little bit of simplifying, and we're going to need this value of mu that we find from the first derivative solution before we can actually continue with this algebra. So again, let's take this expression. Again, ignore the minus sign. We set that equal to 0. These constants are not going to change anything. And so we're left with this sum of xi minus mu equals 0. Well, what is that equal to? Well, it's the sum of the xi's minus 15 copies of mu. And so the sum of the xi's are the sum of all of our initial observations. And again, the sum of mu is mu plus mu plus mu plus mu 15 times. So we get 15 mu. The sum of all of our observations were 967. And so if we move our mu's to the other side of the equation and then solve, we get our estimate for mu to be about 64.47. Now for sigma, again, we're gonna have to simplify a little bit before we can go any further. We can pull out our exponential piece, which is in every single term. And then we can pull out some of our sigmas and our 2 pi to the 15 over 2 and things like that. And what we leave behind essentially is negative 15. Here we had a sigma to the 15 and a sigma cubed in the denominator. And so we were able to pull out a sigma to the 16, because this is now 18, pull out a 16, leave a sigma squared behind, and we still have our sum of xi minus mu squared. And so this is the expression. This can't be 0. This can't be 0. So this is the portion that we set equal to 0. And so we move the 15 over and we start and plug in our mu. And we can use that to solve for sigma squared or sigma. And again, plugging everything in, our best estimate for sigma is 3.0768, because this was our, again, approximately 64.47. That was our 967 over 15. And then when we plug that in and we do the algebra, we get this. Now, these are the same values that we get from other estimation methods. The one thing that is different here is that the sigma is the population estimate. It is not the sample estimate. We ended up dividing by 15, not by, which is the sample size, not by 14, which is n minus 1. This method for this sigma does derive a biased estimate. So these estimates are not in any way guaranteed to be the sort of the best estimate overall, but in most cases, they will be, if not the exact function that we use, you will clearly see how they're similar to the function that we use. But there are these circumstances, like with sigma, where we find that dividing by n underestimates the standard deviation by a little bit, and so we make these adjustments to improve the bias, but they don't derive from these calculations. And you actually see something similar when you do method of moments, which is another strategy for coming up with estimates for parameters based on data, and you see similar things. So most of the time you'll get the function, the expectation that you were thinking that you would get, the formula that you were expecting, but sometimes, like with sigma, you will get one version of the sigma, but not necessarily the one that we use all of the time, because it has other problems. It is an estimator, but it is not necessarily guaranteed to be the best estimator.